Let's have a look at the modified signal flow graph for the feedback control system once again. We have two input nodes, the reference voltage node ER and the load torque TL. We have two output nodes or non-input nodes, omega m, of course, the signal of interest to us, and the armature current IA. And now you can see that there are two loops in this signal flow graph, whereas the earlier one had only one loop. The one without the feedback path had only one loop. Now we have two loops, and so the calculation of the gain coefficients, etc., is going to involve a little more work, and there will be a few more terms that we will have. So what was the first step in applying Mason's rule? To identify all the loops of the graph, and then to calculate or write the expression for the common denominator determinant delta. So that we can do here. We have two loops. The loop gains will be L1 will be given by there is a loop consisting of Ka from E to Ea, then 1 by Kb from Ea to omega m, and then the tachogenerator feedback path from omega m back to E. So that's the loop, and for which the gain will be given by minus Ka Ktg divided by Kb, minus Ka Ktg divided by Kb. There is the other loop from omega m to Ia, and what is the purpose, or the why does that loop occur, or why does that path occur? Because it is multiplied by the coefficient of friction. So this is the torque required to overcome friction divided by Kt, and therefore this is a part of the armature current that is required to overcome friction. One should interpret terms or coefficients that appear on the graph and the various signals. It's not good enough to just do things mechanically, because then only one can understand what's going on and also notice if one has made any mistakes. So this path from omega m to Ia through Kf by Kt once again is because Kf omega m is the frictional torque, that divided by Kt is a part of the armature current that is required. The other part of the armature current is required to produce the load torque, and therefore TL divided by Kt, and that's the summation at Ia. What about the path from Ia to omega m? Why does it occur? That is because of the armature resistance drop. Now that's a voltage which is in addition to the back EMF, and therefore the applied voltage is the sum of the two, or the back EMF is the applied voltage minus this voltage. So that divided by Kb is sort of a part of the speed, you can say, which is used up for the armature drop. If the armature drop was not there, the back EMF would be higher, therefore the speed would be higher. And so what is the gain of the this other loop? L2 is given by minus Kf by Kt multiplied by Ra by Kb. I am not here equating Kt and Kb, although as I told you earlier, Kt and Kb are equal. The back EMF constant and the torque constant for an ideal motor at least are equal. Let's keep them as two separate symbols so that we know what is what. In one place it plays the role of EMF generation, in the other place it plays the role of torque generation. Therefore it's good to keep them separate. So we have these two loops L1 and L2, and therefore we can start writing delta. So delta will be equal to 1 minus L1 plus L2. Just make sure that these are the only two loops that you have on your signal flow graph. That's easy for this graph. Plus, is there a plus term now? Are there loop pairs which do not touch each other? No, because there are only two loops L1 and L2, and L1 and L2 actually touch each other at the node omega m. So there is no additional term. And so this is all that you have for delta, namely delta equal to 1 minus L1 plus L2, and therefore delta is equal to 1 plus Ka K tachogenerator divided by Kb plus Kf by Kt multiplied by Ra by Kb. So this is our expression for the common denominator delta, or the determinant of the signal flow graph. what is the next step? We want to obtain an expression for omega m in terms of the two input signals. One of them is the reference voltage, so an expression which multiplies ER plus an expression which is going to multiply the load torque. Now here also one can anticipate a few things. If the reference voltage is increased, then we expect that the speed will increase. So the coefficient that multiplies ER should turn out to be normally positive. With increased reference voltage, the speed will be increased. Or you can look at it the other way around. If we want to change the speed of the motor, if we want to increase it, then we will have to increase the reference voltage. Or if we want to run the motor at a lower speed, we will have to decrease the reference voltage. What about the coefficient of TL? I have put a plus sign between the two. Now here we expect that if the load torque is increased, the speed will be decreased. Therefore with this plus sign, this coefficient will turn out to be negative, or alternately then we can write a negative sign there between the two terms, then the coefficient will be positive. And let's, as we go ahead, let's check whether we do get these expectations. Okay, so the coefficient of ER, for that what do we have to do? We are writing an expression for omega m. ER is the input node, so identify the forward path from ER to the input node. So ER from the input node omega m, ER to the output node or the node whose signal we are interested in, namely omega m. So what is the forward path? Well, it goes from ER to E and then from E to omega m. Is there only one forward path? Yes, there is only one forward path, as you can check from the signal flow graph. Now what is the gain of this forward path then? It has only two terms, Ka. The error voltage E is amplified to produce the armature voltage capital EA, and then it gets divided by Kb, because that's because of the back EMF effect. And if there was nothing else, then EA divided by Kb would have been omega m. So the gain of the forward path is therefore Ka divided by Kb. So now we are ready to write the expression that multiplies ER. We take the gain of this forward path and then multiply it by the terms in delta that remain when we remove the touching loops. Now what about the two loops? Both of them pass through or touch, have the node omega m. Our forward path ends at omega m, therefore the forward path touches both the loops. As a result, what will survive from delta? We have to remove the loops which touch the forward path. So L1 will go, L2 will go, and what will survive will be only 1. Don't forget that 1. If the paths are named P1, P2, P3, etc., then what survives in the numerator is often called delta 1, delta 2, etc. So if I have to write a general expression for a gain from a particular input node to another node, it will look like sigma Pi delta I divided by delta. There is no particular advantage in writing this kind of a notation if you don't understand it. I very often find students write this thing, but when they want to apply, or when they apply it, they fail to understand what's going on. What does this sigma mean? This sigma means that if there is more than one forward path, then there is more than one term in the numerator. If there is only one forward path, then there is only one term in the numerator. Is it possible that there may not be a forward path from a given node, input node, to another non-input node? It's possible. In that case, what would you put? Nothing, or therefore 0. Then each forward path gain is multiplied by delta I. Now what does delta I stand for? Delta I stands for what remains from delta if we remove those loop gains which touch the path Pi, whose gain is being multiplied by delta I. So choose a forward path corresponding what remains from delta, multiply them together, then go to another forward path, find out what remains of delta for that forward path, multiply those together, add up, and so on. So understand this sigma Pi delta I divided by delta properly, so that you don't go wrong. It's not enough to write an expression, one must know what it means and one should be able to use it properly. So in our case then, what will be the numerator? Numerator is only the forward path gain, what remains of delta is only 1, And so that expression which multiplies ER is ready. I write it again. So omega m equal to something into ER, and that expression, the numerator will be simply the forward path gain Ka divided by Kb, and in the denominator I will have that expression for delta, 1 plus Ka, K tacho generator divided by Kb plus Kf by Kt into Ra by Kb. So that's the expression that multiplies the reference voltage. What about the expression that multiplies the load torque? Now what is the forward path from the load torque node to the speed node? TL to omega m. Once again there is only one forward path, TL to Ia and Ia to omega m. And as I had anticipated earlier, in this path there is a negative sign, which I told you we expect, because if the load torque increases we expect the speed to decrease. So can I then write down, and this forward path, does it touch both the loops? Yes, because it ends at the node omega m, therefore it touches both the loops L1 and L2. Therefore what will be in the numerator multiplying the forward path gain? Only 1. And so I can now do that very quickly, and I can write this as, therefore this is the minus sign. Normally there is a plus sign here. Okay, let me write here plus sign, because this is the normal rule, plus. Then the bracketed expression may have a minus sign, which it does. So bracketed expression is now, as we found out, 1 by Kt, let me write it down, 1 by Kt multiplied by minus Ra by Kb divided by the same expression delta. So this is the complete formula now, giving you the speed of the motor in terms of the reference voltage and the load torque. If we know the parameters of the system, such as the gain Ka, the back EMF and the torque coefficients Kb, Kt, the armature resistance Ra, the frictional coefficient Kf, the specified load torque, the rated load torque, and the reference voltage that is applied, we will be able to calculate the speed of the motor omega m. And if ER changes or is changed, or if TL changes, then we can find out the new omega m, or we can find out the change in omega m caused by a change in the load torque, and that is the quantity in which we were interested. We were trying to reduce the change in speed when there is a change in load torque. The whole idea of introducing feedback was to see whether the change in omega for a given change in TL will be reduced than it would have been earlier when the armature voltage was kept fixed. We will see that very soon. Now when you have an expression like this, complex expression like this, the next step to do normally would be to simplify it by getting rid of the various fractions that you have, and then look at the new expression. Of course, when you get rid of the fractions, the expression looks simple, but then it's very difficult to interpret what each term means. So one should be very careful in simplifying this expression, because a wrong calculation somewhere will upset your whole calculation. So if I now get rid of the fractions here in this coefficient that multiplies ER, then what will I get? I will have to multiply numerator and denominator by Kt into Kb to get rid of the fractions. So if I do that, then I will have in the numerator Ka into Kt, and in the denominator I will have Kt Kb plus Ka K tacho generator Kb plus Kf into Ra. So I get products of several coefficients and added up. As I told you, this now does not immediately have any significance. This whole thing multiplies ER, and then now I will bring that minus sign which was inside, I will bring it outside. So minus the coefficient that multiplies in the numerator will be Ra, that's all, because Kt Kb is what we are going to multiply numerator and denominator, and the denominator will be the same expression that appears in the coefficient multiplying ER. So this is the expression for the speed in terms of the reference voltage and the load torque. The coefficients are all positive, and the expressions that multiply ER and TL are both positive. Of course, there is a negative sign that multiplies the whole thing, that multiplies TL. And so now we see immediately that if TL increases, omega m will decrease. If TL decreases, omega m will increase. If ER increases, omega m will increase. If ER decreases, omega m will decrease. But now from this expression we will see something which, as I told you earlier, is normally interpreted as steady state error. Now let us look at that once again. In the normal discussions in many textbooks, it is asserted that the reference voltage value should be equal to the feedback voltage that will result when the output is at the desired value. So omega t is the desired speed, K tacho generator, omega d is therefore the tacho generator voltage when the motor is running at the desired speed. This is compared with ER, and if the difference is 0, there is no error, and therefore ER is put equal to K tacho generator into omega d. Now we will see immediately on making use of this relationship in the expression that we have derived, that if this is the case, if we set ER equal to KTG omega d, where omega d is the desired speed, then the speed omega m will not be omega d, but will be less than omega d. That is, the drive will not run at the desired speed, even though the tacho generator output corresponding to the desired speed is equal to the reference voltage, or the reference voltage divided by the tacho generator coefficient is the desired speed. Now why is this so? ER equal to K tacho generator into omega d. Now you look at this part, omega m involves ER and also involves TL. So this TL, the load torque, actually reduces the speed. If the load torque is 0, then this term is absent. If there is some load torque, then omega m is even going to decrease. So let us assume that TL is 0, there is no load torque. Even then the motor will not run at the desired speed if ER is equal to K tacho generator into omega d. Can you see why? So for ER now, substitute K tacho generator into omega d. So in the numerator I will have Ka Kt into Ktg into omega d, and in the denominator I will have this sum. Now can you see why omega m will turn out to be less than omega d? That is because what multiplies omega d in the numerator is Ka Kt into K tacho generator. That term appears in the denominator also, but to that are added two more terms which are both positive. So we have omega m equal to Ka Kt K tacho generator divided by the same thing Ka Kt K tacho generator plus some positive quantities multiplying omega d. So because the numerator is less than the denominator, therefore omega m must be less than omega d. So this sort of proves that if you choose the reference voltage equal to the tacho generator voltage produced at the desired speed, then the drive will not work properly. In the sense, it will not even run at the desired speed. I told you that this is absurd, because we can certainly make the drive run at the desired speed under the rated or the nominal conditions. So if we know the load torque, full load torque, let us say, if we know all the coefficients, etc., then we can certainly make the drive run at the desired speed. And so what is the mistake that we are committing here? We are not committing any mistake in the calculations are all correct. The mistake was the assumption that the reference voltage equals Ktg omega d. And so what is the solution to this problem? Well, increase ER. Don't put it equal to K tacho generator into omega d, the desired speed. Choose it sufficiently higher so that omega m is equal to omega d under the rated or nominal conditions. Or alternately, the tacho generator is such that the tacho generator voltage K tacho generator omega d at the desired speed will be sufficiently smaller than ER, the reference voltage that you may have already chosen. Now the mistake was that the ER is the reference voltage which is supposed to represent the desired speed. K tacho generator omega m on the other hand represents the actual speed, and so the difference between the desired speed and the actual speed is the error. For control people, that is the error. For instrumentation people, it's just the opposite. And so the argument is this error should be 0. Ideally you should have 0 steady state error because you want the drive to run at the desired speed. Therefore this error should be 0, and therefore ER should be equal to KTG omega D. But what is not realized is that we have a type 0 system. The motor with the load is a type 0 system. If you apply 0 armature voltage to it, the motor will run at 0 speed. To run it at some non-zero speed requires some non-zero voltage. If that voltage is obtained by the output of a generator, and that generator therefore its field current is being adjusted, then that generator voltage cannot be 0, the field current cannot be 0. So whatever produces or adjusts that field current, namely our error signal E, cannot be 0. But this E is not the error signal. E is just the signal, that's the difference between the reference voltage which represents omega D and the feedback voltage which represents omega m. The only thing is the proportionalities are different. The reference voltage represents omega D with a certain proportional coefficient, whereas the feedback voltage, the tacho generator output voltage, represents omega m with a different proportional coefficient, so that the difference between the two, even when there is no error, even when omega m is equal to omega D, the difference between the two is non-zero. That is amplified, results in an armature voltage which therefore makes the motor run, etc., etc. So there will be no steady state error, but the reference voltage will not be K tacho generator omega D. Or if you insist on using the same tacho generator and the same reference voltage, then you must not apply the whole of the tacho generator voltage to the input of the difference device. You should take only a suitable part of it. Now at this point I would like you to go back and redo some of the calculations that we had looked at earlier, so that you will get some numbers and you will get some figures and see actually what is going to happen. But one can also see what can be done to make, even when ER is chosen as K tacho generator omega D, and I repeat, it should not be, there is no reason to choose it equal to that, but even when it is chosen that way, can we make omega m come closer to omega D? Now look at this expression. We have this term in the numerator which also appears in the denominator, but in the denominator to it are added two terms, namely KTKB and KFRA. Now if we can make those two terms insignificant compared with this term, or to put it the other way, if we can make Ka, K tacho generator KB large compared with KTKB and KFRA, then the numerator and the denominator will be nearly equal. They cannot be equal ever, but they will be closer to equality. And one way of doing that will be to increase Ka. If we increase Ka, then Ka, KT, G, KB will be increased. The other two terms KT, KB, KFRA remaining the same. Therefore, the numerator and the denominator will become more nearly equal than they were earlier. And so, the motor will run at a speed which is still not equal to the desired speed, but closer to the desired speed than it was earlier when Ka was smaller. But then I said that you cannot increase Ka by any amount that you like, because this is only for steady state error consideration. We are not looked at transient error at all, and we will see very soon that increasing Ka will cause some trouble for the transient performance. But we don't really have to do that. We just have to choose an appropriate E reference, ER, or alternately choose an appropriate tacho generator or take an appropriate part of the tachogenerator voltage for feedback, and the drive will operate at the correct speed. However, because of this other term which is present in the expression for omega m, the load torque term, the load torque changes will affect the change in speed. And if we look at the load torque term, what multiplies it, in the numerator we have armature resistance, and presumably the armature resistance will not change by a significant amount. The motor, for example, I said that the motor armature can get heated, but then usually there is a fan on the shaft so that the motor does not get heated too much, or therefore there is some cooling. Therefore Ra is going to remain more or less what it is. In the denominator we have again the sum of those three terms. Now if we want to reduce the effect of changes in TL, then what can we do about that sum? Well, Kt and Kb, we are assuming we are not going to touch them. The field current of the motor is not being changed, therefore that is not going to be changed. Frictional coefficient, certainly we don't want to add to it, and we can't reduce it either. Hopefully it has already been taken care of before starting the motor, that the bearings are well oiled and whatnot. So the only thing that we can do is with the middle term here, Ka, K tachogenerator, Kb, and therefore one solution is to increase Ka. Now what will happen is that when the load torque changes, the drive speed will change, and therefore there will be a steady state error produced when the load torque changes. That is, in spite of the feedback that we have used, load torque changes will result in speed change, and therefore will result in steady state error. But you can compare this with the expression that we had earlier, when there was no such arrangement of feedback, and you can see that the load torque change with the feedback, the speed change rather, because of load torque change with feedback, will be less than the speed change caused by load torque change without feedback. So this Ka, increasing Ka in fact, will reduce the effect of load torque changes, or will reduce the effect of disturbance on the drive. So our type 0 system with a proportional control will give you a situation in which there will be no steady state error under rated conditions when the load torque is at the rated value. However, with change in load torque, that is with the disturbance or with a disturbance signal, there will be a steady state error. So proportional control in this sense gives rise to steady state error because of the disturbance that is present, and there is no steady state error because the drive is error actuated or error driven or whatever. All those statements are not correct. And to repeat once again, that signal E does not represent the difference between omega m and omega d. It is only the difference between reference voltage, which is proportional to omega d, and the feedback voltage, which is proportional to omega m. But the two proportionality coefficients are different, they are not the same. Therefore E does not represent error, although for convenience and most textbooks will call it the error signal, but that is not correct. Now the next thing that we can do is to see what other kind of feedback can be used so that we can get over this difficulty that load torque changes, that is disturbance signals, produce steady state error. How to do that? And I mentioned other schemes of control such as integral control and derivative control. But before we do that, we will look at the same situation from the block diagram point of view, because I don't want you to get the impression that you have to draw a signal flow graph and then only you are able to do something. You can do things with a block diagram also. In fact, we will see that for the block diagram that we will draw, which will be so simple that we will sort of use the signal flow graph rule, as it were, with the block diagram itself. So the block diagram itself can be read as a kind of a signal flow graph if one is careful. So you don't have to draw a signal flow graph, although one could and one should draw it if it helps. So that's the next thing that we would like to do. and but as I told you, you should go back to our original design data and work out some numbers so that one gets some idea of what's going on. What about the set point changes? As the expression shows, omega m is directly dependent on ER. So if you want to increase the speed at which the motor is to run, increase ER to a suitable value. If you want it to decrease, decrease ER to a suitable value. So our drive is capable of operating at any desired steady state speed, and it can be set by setting the reference voltage. So this reference voltage setting, of course, as I told you, is not done by watching a voltage or reading it with the help of a voltmeter and so on. You will have some slider or you will have some knob on a surface on which the speed will be marked, and so what a person has to do is, just as we set an air conditioner, you turn that knob and make it point at the appropriate place, so that the set speed, the desired speed, is set that way. So our drive with feedback then provides for setting of the speed. That part is not automatic. Somebody will have to set the speed manually. Somebody will have to select the position of the knob or the reference voltage manually. But then our drive reduces the effect of torque changes on the speed. So in this sense, use of feedback has improved the performance of the drive. Under rated conditions, the drive will operate at the rated speed. So the drive will work perfectly under rated or nominal or the conditions which were used at the time of the pre-calculations or the pre-programming. Now let's do it with the help of block diagrams. Let's see what is the difference and what things are similar. Earlier I had drawn only one single block like this with two inputs EA and TL, and with two outputs omega m and armature current. I had drawn only a single block. I did not write anything inside the block, but I said that you can write down the two equations that govern the behavior of the system. Now we can improve a little bit on that by drawing a somewhat different block diagram, and we can make use of some of the ideas from signal flow graph analysis that we have studied. And as I said earlier, it's almost like drawing a signal flow graph, except that I am going to show blocks. So the voltage equation, armature voltage equals back EMF plus the armature voltage drop. I will rewrite it, or after thinking of rewriting it, I will draw a different, or I will draw a block, or you will see if there is one block or there is more than one block. On the block diagram also, as you have seen earlier, the various signals appear, EA, omega m, TL, IA as input signals, output signals of the various blocks. Okay, so let us make a beginning. So I will show a block which is going to be like our difference device. So the symbol for that is not really a rectangle, but it is a circle with the four quadrants shown in the traditional way. To one of the quadrants I will mark it with a plus, I will give EA as the input. To the other quadrant, and I will mark it with a minus, I will give an output coming from omega m. I am just showing that signal omega m as an arrow coming out. I have not attached it to a block right now, but suppose the signal omega m is available, then from omega m through a block, now here a block is appearing, although it could be regarded as a coefficient or a gain, I have KB. So this block has omega m going into it, and therefore coming out of it will be what? Will be a signal of value KB into omega m. Now I told you that this is not really a physical signal. When the motor is running, it is extremely difficult to measure this KB into omega m. Although one can measure omega m easily, but as voltage, the back EMF cannot be measured while the motor is in operation. It is something which, according to Faraday's law of induction, is produced while the motor runs. Kb omega m therefore is not a physically measurable signal, but it is a term which appears in the equation. So this goes into this circle with a minus sign. Ea is the other term, the input signal to this circle with a plus sign. Of course this circle is nothing but our difference device. So we see it, if we use it here again, then the output of this will be what? Will be Ea minus Kb omega m. Now that is related to the armature current. So I will put here a block whose coefficient will be 1 by Ra, and that will give rise to the armature current. So I have represented the equation Ea equals Kb omega m plus Ia Ra in this peculiar fashion. It is obvious, but it is worth mentioning that these blocks do not represent some actual physical systems which are connected in some particular way as shown on the diagram here, but they are a way of representing the equation which we wrote for the armature circuit, Ea equal to Kb omega m plus Ia Ra. If we understand these blocks correctly, then from what I have drawn so far, what follows is only that equation and nothing else. Now it is time to look at the second equation, and the second equation has the load torque, the frictional torque, and the torque generated by the motor. Now you can expect how I am going to add to this block diagram that I have already drawn some more blocks, so that equation also will be represented, and therefore I will have both the equations represented on a single block diagram. So what is it that we should do? On this block diagram I already have the armature current Ia, so multiplying it by Kt will give me the motor torque. So I just have to put one more block there, and I will do it soon, and I will have the motor torque. That motor torque is equal to the load torque plus the frictional torque. So I can think of the load torque being subtracted from the motor torque to produce the torque that is left for overcoming friction. Now this is very funny, because the purpose of the drive is not to overcome friction. The purpose of the drive mainly is to overcome the load. The friction is the unwanted part of the load. But for drawing the block diagram, this seems to be a convenient way of doing it. So if I were only to look at that part of the block diagram, then assuming that Ia I have got somehow, I put this block Kt, so that produces what I had called earlier Tm, the motor torque. From this motor torque, now once again this difference device will make its appearance, this circle will make its appearance. From Tm I will subtract TL, and so the difference will be Kf omega m, and therefore the output will be Kf omega m. Once again, Kf omega m is not easily measurable physically. The torque required to overcome friction is not easy to measure physically while the drive is running, but as a signal it is a meaningful thing, and essentially therefore what we are writing is terms in the equation Tm or Ktia equal to TL plus Kf omega m. What we have done is we have transposed the term Kf omega m to the other side, so it looks like Kf omega m equal to Tm minus TL. But I am not interested in Kf omega m, I am interested in omega m. So put a block 1 by Kf, and that will produce omega m. So this block diagram by itself will show or will represent the second equation, and now it is just a question of putting the two blocks together to produce a single block. It is somewhat like what we did earlier with signal flow graph. With signal flow graph we had one signal flow graph representing the EMF or the voltage equation. We could think of another signal flow graph representing the torque equation, and then we combined the two signal flow graphs together to have a signal flow graph in which all the signals appeared, but not as two separate diagrams but as a single diagram, and the equations were correctly represented. In the case of the signal flow graph, each node other than the input node represents an equation or a summation. Here this circle device, which in this case we are interpreting as a difference device, represents an equation, and there are two of them, one for the armature circuit equation and the other for the torque circuit equation. So putting these two equations or the two blocks together, I will draw the composite diagram, and you should try to draw it by yourself now without looking at what I am drawing, by going through the thinking once again. So how do we start? We start with armature voltage. So here is armature voltage. Then from that I am going to subtract the back EMF to produce a voltage which divided by RA gives me the armature current, that multiplied by KT gives me the motor torque. From that, subtracting the load torque leaves the frictional torque, so that divided by Kf produces the motor speed omega m. But I should not forget about those two subtractions that took place. So one of them took place here, and that is the thing that I have drawn, line from omega m to Ea, and I should of course put Kb there, not a direct line but Kb. So let us check. At this difference device, Ea minus Kb omega m is something which divided by Ra is equal to Ia, that is correct. At the other, coming in is Kt into Ia minus TL, that divided by Kf is omega m, that is also correct. So we now have a single block diagram which represents the two equations. Instead of a single block which had two input signals and two output signals, now I have a block diagram which is different and which has several sub blocks. Now this particular difference device, is it feedback and is it negative feedback? Because the minus sign would make one say that it is negative feedback, but is it negative feedback or is it feedback? Now the answer would be yes and no. No, in one sense, that it is not something which has been introduced by us after thinking of open loop, closed loop and all that stuff. It is a part of the operation of the motor. Current in a conductor in a magnetic field, in the presence of a magnetic field, experiences a force. So that produces the torque of the motor. Unfortunately, the moment you have motion and you have current, that produces this back EMF, and therefore we have this term Kb omega m. So in this sense you can say it is feedback. That is, the fact that the conductors are moving does change things electrically. The armature voltage gets opposed by this back EMF, and therefore a much smaller current will flow in the armature than would have flown if you had applied the armature voltage and the motor was not running or the motor was at standstill. And of course that is something one should never do. You should not turn on a DC motor with full armature voltage on. You have to have a starting resistance, as we had mentioned earlier. So this block does and does not represent feedback. It is not introduced by us as a part of the control system. It is a part of the behavior of the motor itself. What about the second difference device? That's certainly not anything like feedback. The load torque cannot by any stretch of imagination be looked upon as a feedback signal or whatever. Now that thing also could be changed around a little bit. At this point I don't want to do it, and we can make another loop appear in this diagram, although right now only one loop appears in this diagram. That loop is from the output of this difference device. In fact there is none, there is no actual difference device. This signal at this point is also not a signal which is physically measurable. So I should not even call it E, but whatever that signal is, from that signal through the block 1 by Ra to the armature current, through the block Kt to the motor torque, through this again second difference device, through the block 1 by Kf to omega m, and then through the block Kb back to the first difference device. So we have a big loop, and therefore I can now convert this block diagram into a signal flow graph if I wish. In fact, it will be very easy to convert it into a signal flow graph. Why don't you try it? I will do it, and you also try to convert the block diagram into a signal flow graph. We have to put nodes corresponding to the various positions, and then just put transmittances on edges that join these nodes. So if I start with the node EA, then there will be a transmittance of 1 to the next node, for which there will be this Kb omega m coming. So here is the output node omega m, of course, and Kb omega m with a minus sign, so I will put here minus Kb. So this 1 and minus Kb takes care of that difference device. So that is the output here, but that is multiplied by 1 by Ra. So that is the next signal which is identifiable as the armature current, multiplied by Kt is the next signal that can be identified as the motor torque. Then we have the load torque as another node. So coming from TL with a gain of minus 1 and from Tm with a gain of plus 1 is the next node, and the node signal here can be identified as the torque required to overcome friction. So from that then I will have 1 by Kf, and that is the back to the output signal omega m. So this will be a signal flow graph that results from starting with the block diagram and then transforming it into the signal flow graph. You can compare this signal flow graph with the signal flow graph that we had drawn earlier and find out whether the two signal flow graphs are really the same, except for redrawing. The arrangement of the nodes is a little different, but the signal flow graphs are the same or they are not the same. Of course, the nodes EA and TL appear in both the diagrams. The nodes omega m and IA appear in both the diagrams. Now I can apply Mason's rule to this signal flow graph, which is also correct, and I obtained it from the block diagram, to get an expression for omega m in terms of EA and TL. And of course I should get the same expression. What is the delta for this signal flow graph? This time how many loops are there? There is only one loop, right? There is only one loop. So what is the loop gain? Simply take the product of these terms, 1 by Ra into Kt into 1 by Kf into minus Kb, that is the loop gain. Since there is only one loop, the denominator delta is very easy to write, it is simply 1 minus the loop gain. So delta will be equal to 1 minus, but there is this minus sign on this transmittance, so I will get 1 plus, and I will have Kt into Kb divided by Ra into Kf. So that will be the delta. What is the forward path from, say, EA to omega m? The forward path from EA to omega m is this straight path. There is only one forward path. The loop touches that forward path. Therefore the numerator will be only the forward path gain, which is 1 by Ra into Kt into 1 by Kf. And so with this we are ready to write down the coefficient that multiplies EA in the expression for omega m. Similarly, the expression that multiplies TL, and you can do this and check that it agrees with the result that we had got earlier. It should not be different. If it is different, then we have made a mistake somewhere, and therefore one should go back and check each and every step of our argument. Now this is for the system without feedback. Now what if I have feedback? Then what is going to happen? If I have feedback now, the armature voltage is not being directly applied, but is produced as a result of that motor generator set, and therefore we are represented by the gain Ka. The signal that is input to that block Ka we called E, and that E was the difference between a reference voltage Er and the feedback voltage K tachogenerator omega m. So what I will have to do is then, on top of this signal flow graph, I will have to add the whatever that is required to represent what additional thing we are doing, or if I go back to the block diagram, I will have to add the blocks that represent this feedback action. So if I do it with the block, then what is the feedback action? Well, Er is the reference signal, then there is this difference device plus minus as usual. The input to that comes through K tachogenerator block from omega m, so that is taken care of that way. So here is the difference Er minus K tachogenerator omega m, and that we call the signal E is amplified by Ka to produce the voltage Ea. So this additional thing I will put on top of the original diagram to get the complete block diagram for the system with proportional feedback arrangement. Similarly, I can draw a signal flow graph that stands for all this block diagram representation and add that to the signal flow graph, and I will get the signal flow graph for the system with proportional feedback. So do that and then apply Mason's gain formula or Mason's rule and check whether you get the same result that we had got earlier. Well, let us only note one thing, that is, when you draw the total block diagram or the total signal flow graph, then as happened earlier, two loops will appear. The block diagram or the new signal flow graph that we will obtain will have two loops. So I will just show them very schematically like this. There is one loop and then there is one more loop. One of the loops goes from omega m through a transmittance minus Kb, that is the back EMF loop, so to speak. The other goes from omega m through minus Ktg, that is the explicit actual physical feedback signal, the tachogenerator voltage output. And so we have a block diagram or we have a signal flow graph in which we have two loops. I told you earlier that in many cases the control system arrangement will result not in just one loop but two loops. But in this case, this loop that appears to come because of this Kb is not a physical loop. There is no physical signal being picked up as Kb omega m and connected to some difference device at all. So this loop is not something physical, it is something only conceptual or in terms of signals or equations or transfer functions eventually. The other loop is a physical loop, in the sense there is the tachogenerator mounted on the motor shaft and you connect the output or the armature of that tachogenerator to this difference device. There is an actual physical connection. K tachogenerator omega m is an actual physical signal. Kb omega m is not an actual physical signal that is measured and then connected to some device whatsoever. So our system still has only one real feedback loop, although on the block diagram or on the signal flow graph two loops do appear. Therefore you might think of feedback being used in two places, but of these one place is just the action of the motor itself. That is the way the DC motor runs. The moment it runs, because of torque, it also produces back EMF. So in fact, as I said long time ago, and all of you should know as electrical engineers, that the motor action and the generator action go on simultaneously. A conductor moving in a magnetic field produces voltage. A conductor in a magnetic field produces force and therefore can result in motion. And so a motor is also a generator simultaneously, or a generator is also simultaneously a motor, and therefore we have to always think of these two equations together: the voltage equation that looks at the voltage or the EMF aspect, and the torque equation that looks at the mechanical aspect of the electromechanical system that a DC motor is.